Okay, welcome to another video for introductory statistics. Today we're looking at the two sample t-distribution techniques. There's two of them. One is a hypothesis test method for comparing two different populations, and the other one is a confidence interval formula that lets you find out how far apart the population means are for two different populations. And so to introduce both of those, I've given you guys a workshop with this I think this is kind of a cool example. It's about cloud seeding, which if you've never heard of cloud seeding, it's an interesting idea. So the idea is that if you spray clouds with certain chemical solutions, the chemicals can start water droplets forming in the clouds and maybe make it rain. And so this is an experiment that was done in the 1970s where they had a plane ready to go that had this silver iodide solution that it would spray the clouds with. And what they did is they used radar to track the clouds and see how much rain that the clouds produced. So on 26 of the days, and those were randomly selected, so there should be no bias here, they tracked the clouds after they sprayed them with the plane, and it produced 446 acre feet. That's kind of an interesting unit there. I guess that's what they get when they used radar to measure the rainfall in the clouds. So it's like acres of area and then feet tall of the clouds that are producing the rain. So they got that much rainfall when they sprayed, and then they got this much smaller number when they didn't spray, 164.6. So just looking at these two numbers, wow, that's a lot more rain when they sprayed, so that really makes it look like cloud seeding is working. But then if you look a little bit more closely, you notice that the two standard deviations are also pretty big. With a standard deviation like that, there's a lot of variability here, so it could be that maybe this difference is more of just a random fluke than a real difference in the, like if we were to do this over and over again many times in the population of all the days you could ever spray clouds, maybe wouldn't see such a dramatic difference. In fact, maybe there would be no difference at all. And so that's going to set us up to do a hypothesis test to find out, is this really a real difference or could this just have been a fluke? That's exactly the question that a hypothesis test is designed to answer. So we have this new technique, this two sample t-test, and here are all the details. We're going to use this formula to find a t-value, and the hypotheses are pretty much always going to be the same, the null and the alternative hypotheses. The null is that there's no difference between the two population means, and that the alternative is that actually maybe there is a difference. So let's go ahead and start answering the questions on this worksheet. So first of all, what are the hypotheses? So the first hypothesis, the null hypothesis, is that there is no difference between the two population means. I don't know how to type a mu into my computer, but I do know how to copy and paste one if I know where one is. So you can just go to the file and copy the mu and then type it in by pasting. All right, so the mu for the two groups. The first group is the treatment group, so I'll write mu underscore treatment. There's no E there. And then it's no different than the mu for the control. So again, paste a mu and then underscore control. All right, so that is my null hypothesis. There's no difference between these two groups. I'm going to copy this and then change it to make the alternative hypothesis. And so change this to an A, and then I need to change this into a not equal to, but actually if I think about it a little bit, the whole idea of cloud seeding is that by spraying a chemical into the clouds, you're going to start rain droplets forming because they're going to sort of coalesce around the chemical. And so if it's going to do anything, it should increase the amount of rain. So when you treat the clouds, you should get more rain than when you leave them alone. So this is a one-sided t-test. I think that's okay to do it one-sided. Okay, so there we go. Those are my two hypotheses. A null that there's no difference, and an alternative that there is a difference. Okay, and unlike when we had a one sample t-test where we had a single group and then we knew what the number should be, now there's no one number, but that's okay. The formula is going to handle that for us. Okay, so now what is the t-value? So we go to our list of formulas, and one thing I've done is I've actually created, if you go to my website, let's see, so let's actually do that right now. Let's go to my website. So here's my website. Go to statistics. On the software tab, I've given you a whole bunch of these different tools, and one of the tools that's really useful for what we're doing now is this interactive formula sheet. So what I've given you here is all the different formulas for doing different kinds of inference, either hypothesis testing with t-values or confidence intervals. And now this week we're introducing these two new formulas, one to do a hypothesis test, one to do a confidence interval for the difference between two means. So we're doing a hypothesis test right now. If you click on this formula, instead of having to use your calculator, you can actually just type in the numbers and then hit enter and it'll automatically calculate it for you. This formula isn't too hard to use a calculator for, but it's a little tedious and it's easy to make mistakes. So I made this instead. If you want to use it, you're welcome to use it when you do the homework. So I'm going to use it right now. So here's the numbers in this table right here. And so I'm pretty much going to type these numbers into the formula and then hit enter and see what I get for my t-value. So let's go up to the formula. I've got 446 is the first x bar, 446. The second x bar is 164.6, so 164.6. Then the two standard deviations, let's pull those up. It's 650.8 and 278.4. So 650.8, 278.4. And then the two sample sizes were both 26. So that's it. Those are all the numbers. I hit enter, and there we go. That's the t-value. And you can literally just copy this and paste it as your answer to the question. All right, perfect. Now, if you know about t-values, remember that they're kind of like z-values, right? A t-distribution kind of looks like a bell curve. It also represents standard deviations, just like a z-value does, except it's sample standard deviations instead of population standard deviations. So what we have here is we have a bell curve, and according to the null hypothesis, these two numbers should have been the same, so that the gap that we're seeing here is a lot bigger than you would have expected. And this is telling us how much bigger than you would have expected. It's saying on this bell curve, we're about 2 standard deviations higher than you would have expected if the null hypothesis is true. And so if you remember about, standard deviations, 2 standard deviations is about when things start to be significant, but we should really check the p-value to see for sure how significant it actually is. So to calculate the p-value, this gives you the t-value, but then you use the app to get the t-value. So I've already done that here. I've got the degrees of freedom. Now, the degrees of freedom when you do a 2-sample t-test is the smaller sample size minus 1. In this case, both sample sizes were 26, so the smaller sample size minus 1 would be 25. I've typed in my t-value right here, 2.0271, and then I want the probability of getting a result as extreme or more than what we got. So in other words, this right tail of the distribution is our p-value, and you can read off the number there. It's about 2.67, or if I round that, about 2.7%. So the p-value equals 2.7% if I round to 1 decimal place, which is good enough for p-values. Okay, so what does that all mean? So we did a hypothesis test. We started with a null. We had an alternative. We had a t-value. We had a p-value. And the important thing about the p-value is that it's below 5%. So that's starting to be significant evidence that maybe we should reject the null hypothesis. Maybe what we're seeing here with these numbers is that this is not just a random fluke, right? Because if this was random, it'd be the kind of thing that would only happen about 2.7% of the time. So I'm starting to think that's not random because that's unusual. So I'd say this is, well, it's evidence, but it's not super strong evidence, right? We're just barely below 5%. So let's say that this is moderate evidence that we should reject the null hypothesis, which means that the treatment is going to produce more rainfall on average than you would get if you didn't spray the clouds. So I guess this is moderate evidence that cloud seeding works, right? That it makes more rainfall. Okay, so that's interesting. So we're leaning towards thinking that cloud seeding works. So a good follow-up question is, okay, so if it works, how much more rain do you get? And that's where a confidence interval comes in. So let's go back to the formula sheet. Now, to make a confidence interval, we would use this formula. And in order to use this formula, we're going to need all the same numbers that we had before. We're also going to need a t-star, a critical t-value. And that comes from the t-distribution table, which I have right here. So I'll click on that. The t-distribution table, you decide what level of confidence you want. I want 95% confidence. And then you look down to find the degrees of freedom. degrees of freedom here are the same as the smaller sample size minus 1, so 25 degrees of freedom. And then you look over to where those two line up, and they line up right here at 2.060. So when I go to my formula sheet, I can just type in the t-value of 2.060. You don't even need the last O. 2.06 is my t-value. And then all the other numbers are the same, 446 versus 164.6. And the two standard deviations, you can go back to the table and look those up. It was 650.8 and 278.4. And the two sample sizes were both 26. Okay, if you hit enter, then it tells you the difference between these two numbers was 281.4, which is our best guess for what the gap is in the population means. But then our guess might be wrong, so here's a margin of error for how far off target we might be. And it's 285.96, which if I round that to one decimal place, that becomes 286.0. And what I should do now is I should add and subtract these two numbers to see what the the beginning and the ending of the confidence interval is. So I've got a calculator right here. Let me do that. So 281.4 plus the margin of error, which I rounded to 286.0. If you add these two numbers together, I get 567.4. And so in my answer for what the confidence interval is, I can say I'm 95% sure that we get between this number, I thought I'd copy that, but I didn't, 567.4 acre feet more rainfall. And let's do the other number now on the calculator. So we go back to the calculator, clear that, type in the same numbers from the formula, 281.4, so 281.4, and then this time it'll be minus 286. And so when you subtract it, well, that's interesting. Now we get a negative number, and a negative number would mean that we're getting less rain when we spray. So let me type that in. Okay, so and negative 4.6, so that's 4.6 less acre feet. I better hit a new line here. So less acre feet of rain when we spray clouds versus when we don't. And one more important thing here, this is the difference between the two population means. So this is going to be what happens on average, not what happens any individual times. So we should just put on average at the end. So there we go. So this is our 95% confidence interval. It's between 4.6 less acre feet of rain and 576.4 more acre feet of rain when you spray versus when you don't on average. Okay, so that's how a two-sample confidence interval works. Real quick, I should also double check that the conditions for doing this are satisfied. First of all, they say that these were random decisions about whether to spray and not to spray. So that's good. That means that there shouldn't be any sample bias in our data. So that's the first assumption. And then the second assumption is that the data has a normal distribution. Now, it actually turns out, if you actually look at the data here is not normal at all. It's very much skewed right, because on the days when they spray, a lot of times it didn't rain at all. And then sometimes they got a big deluge of rain. And then same thing on the days when it didn't spray. Sometimes they would get a little bit of rain, and sometimes they would get no rain at all. And so the distribution in both cases is very skewed right. But that's actually probably okay, because the sample sizes here are both 26, which individually aren't that big. But if you add them together, that's 52. And 52 is enough. It's over 30. It's enough that we can start to say, yeah, that's a big enough sample size that we probably don't need to worry too much about normality. So we can probably trust this confidence interval. And we can also probably trust this hypothesis test. So it looks like cloud seeding works. The evidence here is moderate that it works. How much it works, though, we can't really say for sure. It might produce a lot more rain, or it might only produce a little, or maybe not even that much at all, maybe even none, right? Because this confidence interval included the possibility you get less rainfall. So our evidence here is not super strong, but it's reasonably trustworthy. Okay, so that's how two-sample techniques with the t-distribution work, both confidence intervals and hypothesis test. As always, let me know if you have any questions, and we'll talk more. We'll do some more examples next time now that you've seen this first example. Okay, take care.